So the next speaker of today is Flaminia Giacomini. Flaminia is a postdoc at the Perimeter Institute for Theoretical Physics, and she's very well known for her works with quantum reference frames, and perhaps one of the most well-known people by this work. So Flaminia, please, the floors are yours. She's going to talk about quantum superposition of massive objects and the nature of gravity in quantum theory and beyond. Sorry, the floor is all yours.
Thank you very much for this very nice introduction. And thank you also for the invitation to speak here. It would be nice next time to meet in person. The topic of the talk today is going to be something that we have already discussed largely on in this session. And I would just like to add to the discussion. And I'm going to do that by showing you these different works that are here. And these are two different perspectives on the scientific question. So let me start though with a more concrete motivation than what has been talked about today. So this is an experiment that was performed last year in Markus Aspelmeyer's group in Vienna. And in this experiment, they measure the gravitational coupling between two spheres, and you can see these spheres here, that weigh as little as 90 milligrams. And so why are they doing that? So in experiments, there are two different directions that people are trying to follow. One is to measure the gravitational field of objects that are lighter and lighter. And this is the record as far as I know now. And on the other hand, they try to put massive objects in a quantum superposition and keep them there for as long as they can. So in the end, the hope is that these two regimes will be bridged. And this means that the goal is to measure the gravitational field of a quantum object that is in a quantum superposition of positions. And why is this interesting? This is interesting because this could provide a new observational window on quantum effects in gravity. And now our task as theorists is to understand the theoretical implications of these type of tests. So this is not a new question. This question has been around at least since 1957, when Richard Feynman at the Chapel Hill Conference proposed a thought experiment that involved the mass in a quantum superposition and concluded that if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. But Feynman gave a very precise meaning to what he meant by gravitational quantization, and that is that the state of the gravitational field is in a quantum superposition. So that for him was his definition of gravitational quantization. Since the Chapel Hill Conference, there has been a lot of debate, and many people, also people who I have seen among the participants of the conference, contributed to this debate. I do not have time to go through the debate, so let me just flash forward to 2017, where there were these two papers that have already been discussed that came out on the archive on the same day, and that proposed an experiment to entangle two masses via the Newtonian field. And as has been already mentioned previously, they used the LOCC argument to conclude that the gravitational field is not a classical channel. So, and we have already seen that there were a lot of reactions to this argument. And so let me just add on to what has been said so far with a few more points about this debate. So one of the objections that was raised is that the Newton potential is just gauge. What do I mean by that? This means that the gravity is a gauge theory, and then if you want to recover physical statements, then you have to choose a gauge. And the Newton potential is what remains if you fix, in particular, the Coulomb gauge of the gauge freedom. And then this is not something that you quantize, it stays there. So what you're testing with these experiments would be just the effect of the matter being quantized and not of gravity. So of course, this is a good analysis, but one point that I think we should keep in mind is that the split is not physical. So we could choose other gauges in which the Newton potential is represented differently. So this is a subtlety. And the second, a second objection, and I'm not aiming for completeness, so there will be objections that I will leave out, is that this experiment can be fully explained by considering just gravity as an interaction at a distance. And this is a little bit different to the first objection, because interaction at a distance does not even imply that, so does not presuppose that gravity is even like a field. We just write, for instance, a retarded potential, and we can just describe gravity, the effect in this way. And this is true. However, we can devise additional protocols that have more subtle conclusions, and we are going to see that in the next slide. The third objection is that we cannot assume a theory, basically, to deduce the conclusions of the theory. So, of the experiment, sorry. So in other words, we cannot say this is the theory and then the experiment proves that this theory that I assumed in the first place is correct. So there are alternative explanations of the same effect, and as long as we have equivalent explanations, then we cannot choose one on top of the other. And so I'm going to propose another way to see this question. And I'm going to propose in particular a theory-independent no-go theorem in this talk. And finally, an objection has been raised as to that this is not the correct regime in which to describe the gravitational field and the effect. However, if we think about the equivalent electromagnetic case, there are quantum optics experiments that basically we can treat exactly in the same regime. So I think there is a very good match between the electromagnetic and the gravitational case in this experiment. Okay, so let me now move on to the thought experiment. So this is contained in this paper here, and Alessio and Czaslaw are in the audience, and then there are other authors. And and the thought experiment is basically the gravitational equivalent of this experiment, this 2016 paper here, that derived basically precisely the same thought experiment, but for the electromagnetic case. So here, I would like to emphasize that we are choosing a specific formulation, which is linearized quantum gravity. So here, G is a field, and there is no interaction at the distance. How does this thought experiment work? Long before the start of the experiment, we prepare A, that is a source of the gravitational field, in a quantum superposition of two states that are separated by this distance d. So at the time, when the experiment starts, the gravitational field has already settled in all the region that we consider for the thought experiment. So basically, the interaction is exactly Newtonian. And we are making no approximation here. At a distance, capital D, from the center of mass of A, we prepare another test particle. So this is not the source of the gravitational field, B, that is initially localized in a trap. So it cannot move. And then initially we can write the state of the A, the gravitational field, and B as a two-body entangled state of A and the gravitational field, where L and R stand for the position left or right of the state, and alpha L, alpha R is instead the state of gravity. And B is the initial state of the particle B in the trap. Now, at the initial time of the experiment, B can decide whether to release the trap or not. So it can switch off the trap. If B does not release the trap, then the state is going to be the same for the whole time of the experiment. But if B switches off the trap, then the state of B will start becoming entangled with A and the gravitational field. And after some time, that is the time it takes to become entangled, we have a three-body entangled state. then A can decide at some point during the experiment to close the superposition. And if now, in this case, if B releases the trap, we have a three-body entangled state. If B does not release the trap, B is not entangled with A and the gravitational field. So in principle, by performing an interference experiment, A can know whether B opened the trap or not. And now the question is, can A know this before a light crossing time? If she can, then we have a problem with faster than light signaling. So we expect that A cannot know before a light crossing time, because here we are in linearized quantum gravity, everything should work. And in fact, she cannot know that, but we need to call so we need to have two limiting effects that limit A's ability to know whether B opened the trap or not. The first one on the side of B is a limitation to obtain which path information, namely, we can roughly see this as B can be considered entangled with A under the gravitational field. The second one is that A has to be limited in the possibility to observe interference. So now these two effects are here the vacuum fluctuations of the gravitational field, and here the emission of gravitational radiation in a quantum state. So as you can see, we had to call in order to avoid faster than light signaling, two effects that are typical of a quantum description of the gravitational field. So our conclusion is that the interaction by the Newtonian field is not as harmless as it seems, and there is a quantum information content of the Newtonian field to the Newtonian field. And just to add to that, I also encourage you to attend Dane's talk later, and he has done two follow-ups of this, and so they have more they have a full watertight proof of this protocol. So the take-home message is that in the specific formulation of gravity, we needed to consider vacuum fluctuations and the quantum state of radiation in order not to run into any contradiction with faster than light signaling. So the argument is that the Newtonian potential has a quantum information content, has its own quantum state, and should be considered entangled with the source of the gravitational field. And if I've not convinced you with this thought experiment, then you can also check out this recent paper where we explicitly derive that the phase accumulated in the BMV experiment is described as so there is a quantum state associated to the gravitational field that gives rise to the BMV phase in the gravitational induced entanglement experiment. Okay, so we can still keep a classical description of gravity, but we need to drastically modify the theory. And there are, however, a few caveats on what this result does not show. And so we do not conclude anything on whether the gravitational field should be quantized, because there are, of course, alternative explanations of the effect that we cannot constrain with this thought experiment. So what we show is that within a specific formulation, a fully classical explanation cannot be adopted. And so now the question that I want to ask is, can we instead constrain the theory? Can we have a more theory-independent argument to show that there is something quantum to the gravitational field? And so the question that we asked in this other paper is, provided that we observe gravitational induced entanglement in the laboratory, which conclusions can we draw on the nature of the gravitational field? And we use a theory-independent approach that is typical of generalized probabilistic theories. The core of generalized probabilistic theories is that we have an operational representation of a physical theory that is characterized by the probabilities, meaning the clicks of a detector. So we do not want to make any ontological commitment on what the theory should look like, but we just talk about what we observe in the lab. And there are three procedures that we use, which are preparation, transformation, and measurements. So let us take a general GPT system S. And a general GPT system does not specify whether it is classical or it is quantum. We have no assumptions on that. Then this system is characterized by the set of states, which are operationally equivalent preparation procedures, the set of linear transformations on the set of states, which preserves the set of states, and then the state of effects, which are operationally equivalent measurement outcomes. Okay. We will see that when we impose conditions on measurements, then we can determine whether the system is classical, quantum, or something else in our case. So this is the no-go theorem, and let me read it out. So we consider two non-classical systems, A and B, initially in a separable state, and the gravitational field G. We assume that the systems A and B only interact gravitationally. Then the following statements are incompatible. 1, the gravitational field G is able to generate entanglement. 2, A and B interact via the mediator G. 3, G is classic. So I need to specify some of the words and the terminology that I used in this no-go theorem. First, what do we mean by mediator? Because that's something that is not the same in different communities. So here we take a quantum information approach to what a mediator is. And so this means that if we have three systems, A, G, and B, then the most general interaction that is mediated by G is written as a product of interactions between A and G and B and G. So basically, we cannot have a box which is an interaction between A and B without going through G. This is what we mean by mediator. And this is important because a feature of these experiments is that we cannot measure gravity directly. So at best, we can infer the operational nature of gravity based on how it acts on other systems, in this case, A and B. So the only systems that we can measure are A and B. And then we want to know properties of G just by measuring A and B. So this might look strange, but it is actually very similar to what happens in a Stern-Gerlach experiment, where we do not measure the spin directly, but we measure the deflection, hence the position of the momentum, and based on the deflection, we infer what the spin is. So then I want to characterize what I mean by classical theory, because we need a precise definition of classical in order to say that something is classical or that it is not classical. So here we take, basically this would be the textbook definition, but just with the more complicated words. So a classical system for us is kinematically classical, meaning that any pair of states can be perfectly distinguished. And notice that here there is there are conditions on the measurements that are hidden in this definition. And then it is compositionally classical, meaning that it composes with the standard tensor product rules with other systems, whether they're classical or non-classical. So usually we think about classical and quantum as a dichotomic alternative. So if something is not classical, it's quantum and vice versa. However, in generalized probabilistic theories, these are just two instances of more general theories. So we have classical theory, quantum theory, but then we can have other theories and those that we care about are the theories that coherently, consistently interact with quantum systems. Why? Because so far, to the best of our knowledge, we want to keep the matter as quantum. And so the theorem actually is valid for systems A and B that are more general than quantum. But let's say that we want to keep the systems as quantum. So the only theories that we allow gravity to be are theories that are that consistently interact with quantum theory, namely that they do not map the initial set out of the initial set. Okay. So So this is not to say that we think that gravity should be neither classical nor quantum, but it is a logical possibility. And with this no-go theorem, we cannot logically constrain the system gravity to be just quantum. But something that we can say is we can look at some alternative models of gravity within this no-go theorem and see which conditions they would violate. And in particular,
you have 5 minutes. Sorry.
Great. Yeah, that's the last slide. So in particular, we consider models for gravitational decoherence and collapse models. And in this case, these models would violate the first condition. Then we consider also the Schrödinger-Newton equation, that is a very common model. And this is interesting because it turns out there is a paper by Milnik in the 80s that shows that for the one particle Schrödinger-Newton equation, the space of states has some classical properties. So it's actually not really a quantum system. So there is no GPT at the moment that we can immediately deduce from the Schrödinger-Newton equation for the two-particle case, because it would have very strange composition rules. But we thought of a GPT model that corresponds to the best of our knowledge to the Schrödinger-Newton equation, and we asked for some desiderata. And if there is such a model, then this would violate the second condition. And we can intuitively understand that by knowing that basically the dynamics of the Schrödinger-Newton equation knows about the quantum state everywhere. And so the entanglement, if it's generated, then it would be because the dynamics knows the state everywhere, and not because the gravity mediates it. And then, of course, models such as linearized quantum gravity would violate the third condition. So this is everything I wanted to say. And so I want to close this talk with some questions. The first is, where do we stand in our understanding of the nature of the gravitational field based on these low energy experiments? And we have no conclusive answer now. But we have a lot of interesting observations that are worth exploring. And in particular, I want to argue that we need both these approaches to make progress. And so we need a precise formulation of protocols and experiments in a specific formalism, because this would emphasize the quantum aspects of the description, and it would help us to identify which elements of quantum theory we could probe with these tests. And in addition, this has the potential of relating the superposition of massive objects to the properties of non-classical space-time. And I also want to argue that a theory-independent description is helpful because of three reasons. First, it is robust against modifications of the quantum formalism. So if in the end we find that the theory of quantum gravity is very strange, it is not quantum theory, it's just some strange theory, then these theories are still going to hold. Then it gives us a systematic way to test the internal consistency of the theory. And finally, it allows us to classify alternative models of gravity and see exactly which of the conditions, which of the principles of the theory they would violate. And that is all I wanted to tell you. Thank you for your attention.
Thank you, Flaminia. So now we have some time for questions. I see a question by Igor already, so if you want to go ahead.
Yes, sure. Thank you. Yeah, thanks, Flaminia. Very nice to hear about your work. So I have some question, or maybe to point out some caveats in both parts of your talk. So the first part was the Gedankenexperiment. I just want to mention the following: that you show that the Gedankenexperiment is resolved by including quantized radiation, which is kind of the argument why the gravitational field has to be quantized. And so with my student, we showed in one paper that you can actually apply just the Baimozawa argument without quantizing radiation as well. So it's sufficient, but it's not necessary. This is not to say that it's not quantized gravity, but it's not necessarily kind of a proof that it has to be. So there's other alternative explanations for a single experiment. And a similar caveat, but of different principle. Unfortunately, what my student mentioned, 2 talks ago as well, namely for the other part, namely this action at a distance. You mentioned it as I think as the second or third possible kind of debate issue, that there is an action at a distance possibility of generating entanglement. I think what we wanted to say or clarify is that this is actually dictated by relativity. So Maxwell's equations, QED, quantum gravity, even, they all admit action at a distance formulations. And so it's kind of impossible to remove that loophole, kind of a bit like, Bohmian mechanics being equivalent to something quantum mechanics. So just to mention that, and of course that, that will be in your no-go theorem, kind of the number 2 that I think you had, that there's a mediator. So in these formulations, there's no mediator then in the first place. So it's all consistent, but just kind of to mention that is actually currently, case of relativity.
Yeah, I mean, but that is a no-go theorem. So if, of course, if you can have that it violates the second condition, and then it keeps the other 2. So, yeah. I mean, as long as you stick to a definition of a mediator, then you're bound to the no-go theorem.
Of course, I just mean like in terms of all relativistic theories we have so far, they do have that violation of that second part of the no-go theorem.
You can have it, yes, of course, yes. It's one of the possibilities of the no-go theorem.
All right, thanks. Are there any other questions for Flaminia? All right, so in that case, let's thank Flaminia again.